So we've seen that setting up an area integral, you need to have an area conversion factor. And the conversion factor that you use depends on the representation that you have for the surface. So if you have a parametrization of the surface, so you have some function with 2 inputs and 3 outputs, so that you're getting your x, y, and z location in terms of those 2 parameters, you're going to have bounds on those parameters. Maybe they're simple rectangular bounds, so the 2 parameters each between 2 different constants, or probably the most common case is that one of the parameters is between 2 constants and the other one is between 2 functions of the first parameter, like this. So you would integrate over this region, and the area conversion factor that you'd use, you'd find r sub u cross r sub v and then take the length. So that's your area conversion factor there. Now, if you need to calculate a flux integral, you need to you have a vector field, this would be bold F, and you need to dot it with a unit normal n. So to get a unit normal in this case, r sub u and r sub v are both tangents to the surface. So if you cross them, you get a vector perpendicular to the surface. To make it a unit normal, you divide by the length of r sub u cross r sub v, like that. The second representation we looked at was when you have some function of 3 variables set equal to a constant. So instead of having a parametric surface, you have a level set. So what you do is you project down one of the axes. So you have this projection direction, either it's I, J, or K, and you look at the shadow of the surface when you project down the direction. So if you project down in the I direction, then you see the shadow in the YZ plane and you integrate over that region. Or if you project down the y-axis, so the projection direction is J, then you see a shadow in the XZ plane and you integrate over that region. If you project down the z-axis, then the projection direction is K and you see a shadow in the XY plane, you integrate over that shadow. Now for each little bit of surface in the shadow, you need a conversion factor that would change the area of the shadow to the area of a piece of surface up here, and that conversion factor is the gradient of f divided by the length of the gradient of f divided by the absolute value of the gradient f dotted with the projection direction, whether I, J, or K. Okay, so now if you need to do a flux integral, you're going to need a normal, because you're going to have to do your vector field bold f dotted with that unit normal. And of course, if you have a level set, then the gradient is perpendicular to the level set. So this gives you a normal, and you would just need to make it a unit normal by dividing by the length of the gradient of f. Okay, and then the last case was when one variable was a function of the others. So in this case, you have some domain for the function in, since z is a function of x and y, you have some domain in the xy plane, and then you have the surface floating maybe over it, okay? And you need to find a conversion factor to turn a patch of area in the domain where you do the integral. You need to convert that patch of area to the correct size on the surface, and the conversion factor to use is f sub x squared plus f sub y squared plus 1 underneath the square root. So there's your area conversion factor in that case. So if it were that y was some function of x and z, then you would do the partial of that function with respect to x squared and the partial of that function with respect to z squared plus 1 underneath the square root. Or if it was x that was a function of y and z, then you just do the partial with respect to y squared plus the partial of that function with respect to z squared plus 1. So it doesn't really matter how your surface is set up, it's just a matter of changing the names. Okay, so how could we find a normal? Well, in this case, when you have one variable as a function of the others, you can subtract and get a constant on one side. And now you can think about this as a level set. So we have a function capital F that depends on x, y, and z set equal to the constant 0. So this surface is actually a level set of this function that we just created called capital F. And so a normal would be the gradient of f. Now the partial of capital F with respect to x, this doesn't depend on x, and the partial of this with respect to x is little f sub x, or negative little f sub x, because of the negative sign here. And the partial with respect to y is negative little f sub y. And the partial with respect to z, well, that doesn't depend on z, but the partial with this respect to z is 1. So this gives you a normal. You would just need to divide by the length of that normal, which would be, again, f sub x squared plus f sub y squared plus 1. So for each type of representation, whether parametric surface, level set, or a function where the surface is the graph of that function, then you can set up a conversion factor. So you can integrate over the shadow or the domain of the parameterization, and you can use this conversion factor to get the correct area. So convert the area in the integral to the correct area on the surface. And if you need to do a flux integral, you can set up a normal in this way.